So we're going to look at how to apply a kinematic one-dimensional motion problem using the six-step problem-solving method, FIDESA. So the problem in question states, if a ball traveling 200 meters after experiencing a constant acceleration of 2 meters per second squared for 4 seconds, how fast must it have been initially traveling? So FIDESA required. And this is of a similar setup as some of the homework you guys will have. You will see that it'll be in bold, FIDESA required, when I'm required to write FIDESA. So the F, what is it I'm trying to find? I want to find how fast it must have initially been traveling in terms of an equation that is the initial velocity. So V I, V naught, V initial, however I want to call that. That's the thing I'm looking for. Image. Let's draw kind of what this is doing. So if I have a ball and it's initially traveling, it's going to undergo some acceleration. So acceleration is going to push it this way, and it's going to travel a distance of, we'll say, 200 meters, where this is VI, V final, something like that. Doesn't have to be very specific, just so I understand this is one-dimensional motion, and the ball is either it is initially traveling or it's at rest. I don't know that yet. In fact, actually, we can solve for that. If the initial velocity I calculate is 0, then it would have mean the ball is at rest. If it's not, then the ball was already traveling before the acceleration was applied to it. So D data, all the things I am given. So really, I'm given, I would call it delta x as 200 meters. Now we could just call that distance D. We call it x final, but that's really its overall travel distance as a displacement. So I'm just going to call it delta x. Acceleration is going to be 2 meters per second squared. And then the time I could call delta t or just t. Because time is a scalar, it's kind of inferred both ways. But those kind of mean the same thing. This is then 4 seconds. And it doesn't look like there's really anything else. I can't assume it's initially at rest. I don't know that. In fact, that's actually the number I'm looking for, is the initial velocity. And I don't know that it stops moving, so I can't infer that either. So those are all the distance, the data points that I'm given. In terms of equations, if I look at these variables and this variable, there is one kinematic equation that stands out. X final equals x initial plus v initial t plus 1/2 a t squared from my equation sheet. So that's probably the only one I need. So we'll go ahead and leave the E for equations there. And let's go straight to the solution set. So I'm going to write out my equation again. Equals x initial plus v initial t plus 1/2 a t squared, and I am looking for v initial, so I want to eventually solve my equation for that. You'll notice, though, one thing that's slightly different is I have this labeled as delta x. So if I minus x initial to both sides, x final minus initial of anything is the same as change in, or delta. So this then becomes delta x on the left side as equal to the initial velocity times the time plus 1/2 a t squared. I'm going to subtract 1/2 a t squared to the left. And then I get that the initial velocity times time is equal to the change in position minus 1/2 a t squared. I'm going to divide time. So I get v initial is equal to the change in position over time minus 1/2. This becomes a t squared divided by t. Just makes one of those t's go away. In terms, so that would be my solution, my equation, which is most of the points that your FIDESA homework problems are going to be worth. The last step, A, answers to plug all the numbers in. So the change in position, so initial velocity, change in position is 200 meters divided by 4 seconds. And this gives me a meter per second, which is good. Velocity is meter per second. That's what I want. Minus 1/2 the acceleration, which is 2 meters per second squared, times 4 seconds. One of these seconds cancels. I'm left with another meter per second You can add like terms, both are in terms of the velocities expected units. So it looks good, like we set our equation up properly. The initial is then going to be, this is 50 meters per second minus, these two cancel and I'm left with 4 meters per second. Initial velocity is going to be 46 meters per second. So that's how fast it must have initially been traveling in order to travel that distance with that acceleration applied to it.